Good afternoon, everyone, and thank you very much for joining us today for this webinar. My name is Daniel Franco from Rupert Consult here in Cologne, Germany, and I will be moderating today. I'd like to say that this webinar is organized by the CIVITAS Satellite and CoEXist projects, both of which are Horizon 2020 projects and have joined efforts to reach out to stakeholders all around Europe and the world. And we're very happy to have received such a high level of interest today with over 150 registrations prior to the event. So far, we can see that 56, 57 participants have joined us already, and we're sure that many more will do so through the course of the webinar. And today we will learn about the automation-ready transport modeling functionalities that have been developed within CoEXist, and we will address the challenge of including connected and automated vehicles in traffic flow and in travel demand simulations. Before we start, I would like to explain a bit about the functionalities of our webinar system. If you have any problem with the audio, please note that you also have the option of dialing in. Just click on the phone call option in the audio setting and choose a number from the list of countries that are available. Now this is the GoToWebinar toolbar. All participants are muted as a default setting to avoid any background noises, but you have the chance of raising your hand if you have any comment or questions, and we can unmute you then. The raising your hand button you can find with the little hand and a green arrow. But please do remember to mute yourself again after you post your question during the Q&A session. There's also a question box where you can send us your doubts, your questions throughout the event. One of my colleagues will monitor and record them and post them during the Q&A session. And you can also contact us about any technical difficulties or doubts you might have. There will also be some handouts available, but before that, just some instructions about the questions. You can use the question box featured at any time. We will have 2 moments where questions are going to be taken, so 3 to 5 minutes session after each presentation. And there will also be a 10-minute open discussion at the end of the webinar. And as I was mentioning before, you will also find handouts available for download, including this introductory and audience guide presentation and some other documents from CoEXist. This is the webinar team. Daniel Franco, myself, I'm moderating, and my colleague Sridvina Govender, she's handling the questions and polls that we will have throughout the event. And we have a great set of presenters for today. Peter Sukenik from PTV Group and Jörg Sonnleitner from the University of Stuttgart, both partners at the CoEXist project. Now on the webinar structure, after this brief introduction, we will hear from Peter on microscopic traffic flow simulation, and then from Jörg related to macroscopic travel demand modeling, finalizing with the open discussion and wrap up as I was just mentioning. Now we have decided to invite to this webinar because we do see a great need for tools to be developed and allow for an automation-ready transport and infrastructure planning connection with this automated mobility topic and technology. This is, we believe, a key precondition to enabling and fulfilling the promises that CAV poses on reducing road space demand, improve traffic efficiency and safety. But what do we mean with automation ready? Within CoEXist, we have defined this as the capability of making structured and informed decisions about the deployment of cooperative, connected, and automated mobility. So it's very much in line with the strategic aim of the project of bridging the gap between the technology and transportation and infrastructure planning, of strengthening capacities for urban authorities and cities to effectively address this challenge. And to do so, CoEXist has a three-step approach, and modeling is a cornerstone of this approach. The first step, as you can see, automation-ready transport modeling. Within this project, we have then developed functionalities that allow for the consideration of automated vehicles within both microscopic traffic flow and macroscopic travel demand models, including different types of CAVs and for different automation levels. We also work together with road infrastructure, road authorities, and we're assessing the impacts that CAVs have on road infrastructure in our partner cities. And these are the other two steps of our approach. And for this, I would like to also take the chance to invite you to join us again next year for the next webinar, which we will look at the results of this implementation within CoEXist partner cities. We will look into the assessment of the impact they've had on road infrastructure. This is yet to be scheduled, but it should happen around March or April 2020. And I would like to recommend you to subscribe to our latest news and events by going to our website. This way you won't miss any of the events that we are promoting. And if you want to learn more from CoEXist, you are also encouraged to visit our YouTube channel by going through this link. You can find all the previously held webinars, an introduction to connected and automated driving, which was held last year. Maybe some of you also joined us back then, and more detailed webinars on PTV Visum and Visum softwares and how you can use them to model automated vehicles. I would also like to take this opportunity to invite you to engage with us, to let us know your opinion on CCAM by replying to our survey, going through this link. The survey is still going to be open for a little while longer, and it's a very important input for our work in CoEXist and the conclusions that we're getting to. And to also let you know that the project's final conference is happening next year in Milton Keynes by the end of March. So please save the date, and we'll be very happy if some of you can join us there. We will have also a training on the tools that are being developed in CoEXist. So please make sure to keep an eye out for this event. And before we go then for the next presentation with Peter, I would like to get to know a bit about who has joined us today. We see now 74 attendees, actually. Let's hear from your side what your occupation, your background is. So, Irina, if you can please open the first poll.
Sure thing. All right, you should now be able to see it.
That's the second one. But let's also hear from your side. When do you expect automated vehicles to be available on your city? This is always very interesting to hear because from the different backgrounds that participants have, we've learned in our different events and sessions, the expectations can be quite different, and it is very interesting to see what you expect from automated mobility. Okay.
All right, I'm seeing quite a few people have answered, so I'm going to open up your next question.
Okay, I think we have
All right.
83% now. Yes.
Yep. I'm just going to close the poll, everybody, if you want to have a last few seconds to answer. All right. So we should be able to see the results of the poll.
As you can see, there's quite a mix, but most of you think that it's going to be after 2040 or after 2050. Okay, that's interesting. Good to know.
All right. Shall I move on to the first question?
Yes, the first question. We can go back to that one.
All right.
Okay, so here we would like to, like I was saying before, learn about your occupation and background, whether you're representing a public authority, whether you're a consultant, maybe you work on as a transport operator or mobility service provider, researchers, industry, or if you have any other background, please also let us know in the question box.
All right, just the last couple of seconds. All right.
Great, thank you. Okay, that's also quite a diverse group we have today with a large number of researchers and university staff. Also, we have participants from the industry, public authorities, and consultants and advisors. So a very diverse group. This is very valuable from our side as well to reach out to different groups of stakeholders. So thank you for being here today. And without further ado, we would like to welcome Peter Sukanik from PTV. He will let us know about the functionalities that have been developed in CoEXist on microscopic traffic flow simulation. So welcome, Peter. Thank you.
Thank you, Daniel. So now you should see my screen, right?
Yes, we do. Thanks.
Perfect. So hello, everyone. This is Peter from PTV Karlsruhe, and with me, my colleague Lucas Couch is here, and he will help me to answer your questions later. I will present you new developments in PTV VISIM related to CoEXist project and related to the microscopic modeling of automated vehicles. I will start with the recapitulation of features we already presented and which are included in VISIM 11 already. The first one enforces absolute braking distance, an ultimate safety requirement that is applicable for rail-safe and cautious driving behavior. It is based on brick wall stop distance principle. Next one is use implicit stochastic on by default to mimic the human behavior, can be switched off for automated vehicles. Number of interaction vehicles. Now you can distinguish between vehicles and objects and simulate sensor limitations. For example, the vehicle can see only the preceding vehicle. In that case, you can set the number of interaction vehicles to 1 and the number of interaction objects to a higher value, so the vehicle still can see a signal head ahead. Increased acceleration. A vehicle class can accelerate over the desired value if needed, for example, to maintain tight the following of automated vehicles. Gap time. based on leading vehicle class, you can set different gaps and standstill distances based on the leading vehicle class. Consider vehicles in dynamic potential. Pedestrians can actively look for gaps to cross between vehicles standing or slowly driving. So this is important for the interaction between vehicles and pedestrians in shared space areas or similar areas. Then 0 passengers for automated vehicles. Occupancy distribution with 0 passengers are now available. And OpenDrive import basic network objects like link and connectors from OpenDrive files. If you are interested into details, so please have a look on our previous webinar. Daniel mentioned it already. You can just click on the link and watch the recording. The next one I want to talk about is driving behaviors. You know that since VISIM 11, we have 3 additional driving behaviors in VISIM per default: cautious, normal, and aggressive, based on CoEXist project. And these new driving behaviors have modified parameters which are based on the driving behavior concept. This was developed by Adriano Alessandrini for the CoEXist project and describes 4 fundamental driving behaviors: rail-safe, cautious, normal, and all-knowing. The first one, rail-safe, we didn't implement it into VISIM. That's a very special one, but we implemented cautious and normal. And the last one, all-knowing, we call it inside VISIM aggressive, because it's better described what VISIM can do. And we still call it all-knowing within CoEXist project because it assumes a more complex and higher level of communication and cooperation. And the modified parameters are based also on empirical data. Well, we collected on the test track in Helmond. We collected mostly the data from following process, not from a lane changing process. And the parameters are based also on results from cost simulations, and the cost simulation data was produced by PDV and Vedicom when we have different control driving logic used in a simulation. And of course, we made some assumptions, especially for lane changing. This one is new, implemented in VISIM 2020. It's called lane-specific driving behavior, which means now a link behavior type can be assigned to a lane, and it overrides the link behavior type. So if you define a specific driving behavior for each lane on your link, this will be applied for vehicles driving on this lane. If you don't fill any values here in the link dialog for the lanes, the driving behavior of the link will be used. The next big feature is platooning. Under Platoon, we understand a group of connected vehicles traveling very closely and safely together, also at high speeds. The use case we implemented it for is the simulation of effects on general traffic, and there is no special simulation of Platoon internals or of the internal dynamic inside, or of the vehicle dynamic inside a Platoon. And we developed this feature in a way that there is a stable driving within the Platoon. And there are also a few new driving behavior attributes available you can set. This feature can be set vehicle class specific, so you can let only cars to build platoons, or only AGVs with AGVs, or you can have a mixed platoons. So you as a modeler can decide. You can have platooning also only in one or few lanes on your link. I mentioned the lane specific driving behavior you can set on a link for each lane, and you can use it, for example, to have a platooning only on one link. A few words about Platoon Life Essentials. Joining the platoon, a vehicle can join platoon from behind, not from the side. So the platoon will not make space and allow to join vehicle from the side, from another lane. So only a vehicle from behind, which is driving in the same lane, can join the platoon. And a platoon can be created only by vehicles using the same driving behavior. Platooning is not available for public transport vehicles and not for vehicles on parking routes. There are 5 new parameters you can set for platooning. The first one, maximum number of vehicles in a platoon. Then the maximum desired speed you can set, which will be used by the platoon. So if a vehicle with a desired speed 130 will create a platoon as a leader, then it will adapt the speed to the maximum desired speed if the desired speed of the platoon is lower, let's say 100 or something like that. The platoon will drive with the desired speed of the leader of the platoon if this speed is not higher as the maximum desired speed of the platoon. The next parameter you can set is the maximum distance for catching up to a platoon. And vehicle can join a platoon in the front only if the speed of the vehicle is at least a little bit higher than the speed of the platoon in the front. You can set the gap time in seconds and the minimum clearance. So you can set how big the distance is when driving in platoon will be. The driving itself, the platoon cannot change the lane. So the platoon can continue only in the lane. And if there is a need for lane change because of the route, for example, then the platoon will dissolve. If there is only one vehicle in the platoon or a few vehicles in the platoons or which need to change the lane, then these vehicles will leave the platoon in order to perform the lane change. The vehicles within the platoon, they keep the same distance, which is speed dependent, of course, and there is some kind of limited acceleration change built in. There is a change of parameters possible during driving. So if a platoon will drive from one link to another link, the other link can use another driving behavior. Also for platooning, different values for platooning. So after the platoon will reach the second link, it will adapt to new parameters. And the platoon can split if there is a reason for that. For example, if there is a red signal, it might happen that part of the platoon need to stop in front of the signal, and only the first part of the platoon can continue on green signal. And so there will be 2 platoons. One platoon will continue, and the second platoon will stop at front of the signal. A few words about leaving the platoon. If a vehicle needs to leave the platoon because of the route, for example, because vehicles can form a platoon only if the routes overlap. And if the vehicle needs to change the lane, for example, then it needs to leave the platoon, and the distance before and behind this vehicle will be increased, and then the vehicle will perform the maneuver. So the platoon will split. A few words about platoon stability. Each platoon has a platoon leader, the first vehicle in the platoon, and the last vehicle in the platoon. This one proceeds to keep defined gap time or clearance to preceding vehicle, while the acceleration of this last vehicle is limited to the acceleration of the leader plus minus 2 meters per square second. And the platoon members, these are distributed equally, so the distances between vehicles are same. And as I mentioned already, there is no simulation of some communication processes itself, no packet sending or dealing with latency like in a real world with real hardware. This is the way we implemented it in order to achieve a stable behavior within the platoon without escalating acceleration values or some unrealistic values. Next part is a demo. So let me show you a few examples directly in Vsim. So here I started a simulation, and you can see vehicles driving in and building platoons. Let me explain the colors of vehicles. The dark blue is the leader of the platoon, and the light blue is the platoon member. Vehicles with the dark black color, they are not in the platoon. And this visualization is based on the value of one new attribute, vehicle attribute, which is called indexed in a platoon. And if you would like to achieve this kind of color evaluation, you can set to the drawing mode to use color scheme, and as a into color scheme configuration, you need to pick up index in platoon, and then choose a color you like for platoons. As you can see here, there are different vehicles within one platoon, cars together with AGVs. Why is that? Because if you have a look on link behavior type list, for freeway, I'm using here in this example freeway driving behavior number 3 as a default, and for 2 vehicle classes, which you can see here in a coupled list for a car platoon and AGV platoon, they use driving behavior for automated vehicles. And I set the same driving behavior for both these vehicle classic. And that's why they can build, they can be in a one platoon, these 2 vehicle classes. So now I stop the simulation and I will change for cars to another one, to aggressive, for example, and start the simulation again. And you will see that the AGV will not join the platoon of cars. So there are platoons of cars, and there might be also platoons of AGVs, like you can see here. So This black vehicle can join a platoon, this one not, because it's different vehicle type. So this is a simple way how to have platooning. Let me show you the new tab in driving behavior. On the tab Autonomous Driving, you can allow platooning in your model, and here you can set the 5 parameters I talked about. Okay, let me switch to another example. Here I let a few vehicles to drive into my network, and again the dark blue color means this is my leader, platoon leader, and the light blue are platoon members. And the best possibility, or the easiest way how to form a platoon, is to let the vehicles to stop at the front of the signal. And then when the platoon drives through the network, it comes to a moment where a vehicle, this black one, left the platoon because this vehicle will need to change the lane because we'll leave the motorway here. So you can see that the distances to the preceding vehicle is increased, and also the distance to the vehicle behind increased, and then the vehicle can simply leave the network, and the 2 new platoons can continue driving. And later they can become a 1 platoon again. Here in my case, in my network, they need to stop because of a signal again, and they will form a 1 platoon again. Then this platoon continues through the network, and it can happen in the network that only a few vehicles from the platoon will make it on the green signal, and some of them need to stop. So this last vehicle will not make it on green or yellow, so will stop. This platoon of 4 vehicles will continue through the network and will approach unsignalized intersection, and can happen that a vehicle will leave the platoon like this first one, and we have a new platoon of 3 vehicles behind, because this first vehicle can make it through the intersection, but the rest of the platoon need to wait to give a priority to this vehicle. And then the platoon will continue if there is a gap. And at the end of my example, the vehicles need to make a lane change, which means they will leave the platoon. The platoon is dissolved now. You can see it on a black color. And then later they can create platoons again. Okay, I have one more example to show. This is an example of the Helmond network, and this example will be a part of the installation later, I think in the service spec number 4. It's not in the example directory yet, but it will be added soon. When I start the simulation here, then you can see vehicles filling the network, approaching the signals in a 2D on the left and in a 3D on the right. And again, I'm using the same color for platoons, and the leaders of the platoons are also telling I'm the leader. This with it with using 3D information signs showing this value. And on this example, I would like to show you how you can evaluate the platooning in a simple way. Here in this chart, you can see the number of vehicles in platoon in the network in this first column. Then you can see number of platoons in the network, and then you can see number of platoons of specific size. Platoons of the size of 2 vehicles, 3, 4, up to 8 vehicles. And this is showing dynamically the state in the simulation. And this is done by using a simple script. I will just show the script. So it's quite simple, and it's using the vehicle attribute index in Platoon to calculate the number of platoons and the number of platoons of specific size in an easy way. And this script is saving this information into user-defined attributes. And this chart shows these user-defined attributes. And this will be also part of the example later. So now I will go back to my presentation. I have one more slide to show. We have some new vehicle attributes in VISM 2020. The first one is safety distance, net, which is the desired safety distance, front to rear. Then clearance, the distance to the leading vehicle, front to rear, and following distance, net, the distance to the relevant interaction objects front to rear. You might know that we have a similar attributes for a long time inside VISM, which are gross, which shows gross values front to front, but now these attributes are available, making it easier to examine or debug your model. And also you might need to save these values for post-processing, and you don't need to subtract the length of previous vehicle, and you can save some memory. That was all from my side. And if you have questions, then I'm ready to answer, or my colleague Lucas.
Thank you, Peter, for the very interesting presentation. Yes, we do have a couple of questions on the chat now. So let's first go to a question by Fernando Torres. He asks whether platoons can be set only for specific vehicle classes.
Yes, you can define a driving behavior which will be used only by your vehicle class you define, or by several vehicle classes you define. So you can have a copy of existing vehicle class, conventional class. You can make a copy and say this is my class for automated vehicles, and you can allow forming platooning only for this vehicle class by letting using a special driving behavior by this class.
Great, thank you. Okay, and we also have a question by Ermal Silimani asking whether we can explain again why platoons are so important. Why are we focusing on them during this presentation?
Because we expect that in the future there will be platoons on the roads, and our software, we wanted to make our software AV ready including allowing simulate platooning and all other features which are available for automated vehicles. We presented already in the previous webinar, and this one was focused on platooning, because platooning is the new thing which is available for automated vehicles in VISM 2020, including lane-specific behavior. And actually, right now there are some research programs and some pilots programs where vehicles are tested already on a real infrastructure, driving in platoons. For example, in Austria, there is such a pilot program where trucks are driving in platoons of size of 2 vehicles. And yeah, VISM now allows you to investigate the effects of platooning on your infrastructure in the future, where there will be much more platoons.
Exactly. Thank you. I would like to again remind you that also past webinars are available on our YouTube channel. Like Peter well said, we had a webinar previously where the initial functionalities for modeling automated vehicles were presented. Now, because we wanted to improve these tools that have been developed, there are some new availability of functionalities that allow the consideration of such promising characteristics, such as forming platoons. And this is what is being mainly presented today. But please also visit our previous webinars. And if you have any questions or comments, feel free to contact us via the website of the project. And also you can see now our contact details during this webinar. Let's take a couple of more questions before we go to our next presentation. We have a question from Fotaini Rufanu. Which parameters of the Widerman model were parameterized for developing the 3 AV models? Were additional parameters added for the development of these models?
Mm-hmm. Okay, let me show that in VISM.
Yeah.
So this platooning and platooning parameters are new. What is new is also this option here, use implicit stochastic and enforce absolute braking distance. So these 2 features are new you can use, and for following itself or for car following model, we proposed values for each driving behavior, cautious, normal, and aggressive, and actually we change almost all of them slightly. The normal one, for example, is very similar to the conventional driving behavior parameter set, but cautious and aggressive, there are more visible changes. And we did it not only for car following, we did it also for lane change parameters, but as I said, this is based mainly on assumptions. For car following parameters, we also have some empirical data, and yeah, that's the most important, the parameters under car following model and lane change. You can also have some change for signal control. For example, if the vehicle kind of recognize that they are approaching a signalized intersection, and if you know that they will, based on that information, they will change the behavior, like they will reduce the safety distance, then you can put another factor as 1. And actually, the default value for conventional vehicles here is lower than 1, because it was shown in real traffic that the vehicles are driving a little bit differently when they are close to an intersection. So basically, we propose values for all parameters. You can find it in the deliverables we prepared or in the guide we prepared. And there is a new tab and a few new features like enforced absolute braking distance, use implicit stochastic. And this field here in car following model is new, where you can set following behavior depending on the vehicle class of the leading vehicle class. So you can have you can distinguish, or you can for each combination or for each pair of possible vehicles in the traffic flow, like AV following AV or AV following conventional vehicle or conventional vehicle following AV and so on. For each this combination, you can set different parameters.
Great. Yes, thank you. Okay, I think we have time for one more question during this session. The rest, no worries. We will have another Q&A session by the end of the webinar, so we will save some questions for then. But let's take one last one. Okay, we have here a question by Hisung An. Why did you select the maximum number of vehicles in the platoon to be 8 vehicles? Do you happen to have a special reason for that? So
No,
what
it
are the
was
limitations
just
there, or?
no, it was just demonstration example, and you as a modeler can decide how many vehicles can be in one platoon, or you can investigate what would be the impact of platoon size 3 or 5 or 8, if there will be some difference in capacity or in travel time or delays or some other KPIs. So you as a modeler can set this value, and yeah, there were some. You can find some papers with some experimental trials, and I think they deal with the platoons up to 8. But in VSIM, you have you have the freedom to set any value you want to test.
Exactly, and I think it's important to remember that at least in the functionality that we're seeing now, the platoons cannot change lanes, right? And also there's no cut-ins in the middle of the platoon and so on. So it's something to consider and to investigate. How long would you like to allow a platoon to be in? What the effects on the congestion and the other impacts on the mobility are, right?
Yeah, exactly. And maybe in reality there will be some rules platoons need to follow. For example, they can form a long platoons between intersections, but when they will be close to intersection, maybe they will need to dissolve in order to have bigger distances between vehicles to allow lane changing for other vehicles which want to go out from the motorway. So there might be different scenarios, and you can test them all in VSIM.
Perfect. Thank you very much, Peter, for the interesting presentation.
You're welcome.
So now I think before we go to Jörg, let's have one more poll. Sadrina, can we go to poll number 3 here? We would like to know what you think about these sort of tools, and whether you foresee including CAVs in your city or your organization's traffic flow or travel demand modeling efforts in the near future. So this is very simple, yes, no, or I don't know, not applicable. Okay, I see that almost half of the people have voted.
All right, I'll keep it open for a couple more seconds. All right.
Perfect. Okay, that's great to know that more than half of you do foresee using this sort of tools in the near future. So hopefully this webinar is going to be very useful for your professional activities. Okay, thank you, Sidrina. Let's then welcome Jörg and hear from him on the macroscopic travel demand modeling tools.
Thank you, Daniel. And hello, everyone. I also want to welcome you to the next part of the webinar, which is on macroscopic travel demand modeling. My name is Jörg Sonnleitner, and I'm a research assistant at the chair for transport planning and traffic engineering, located at the University of Stuttgart. So the aim is to present methods to you for macroscopic travel demand modeling. More precisely, we want to demonstrate how to modify existing travel demand models to include characteristics and impacts of highly automated vehicles. So we are not going to talk about the impacts of fully automated vehicles, but about those of highly automated ones. Within the project CoEXist, we developed the tools presented today, and these are applied in macroscopic use cases in two of the project's partner cities, Gothenburg and Stuttgart. And for demonstration, we will use a travel demand model for a simplified study area and show how the methods can be integrated step by step. This will be supported by the use of scripts. These are useful to prepare and build the model, but I will not use them to operate it. It's just faster and more comfortable. And of course, I will explain what they do, and all files used will be available for download, so you can have a more detailed look later. The link will be sent to all of you and can be found in the video description of the recording. We want to present 3 scenarios today. First one, S0, is our baseline scenario where we have no AV at all. Then we will introduce highly automated vehicles and include changes in traffic performance, scenario S1. And the last one, scenario S2, additionally incorporates changes in the perception of travel time. And our expectation is that we see impacts on both supply and demand side. In particular, we expect to see changes regarding travel times, mode choice, and destination and route choice. Now we will have a look at the model. So we see the network of a rural region close to Munich. So we see part of Munich on the bottom left. And for the traffic zones, there are bars displayed which show the inhabitants, employed persons, and working places for each zone. So this means that the structural data is already included in the model. Furthermore, we see the road network, and the roads are classified by the roadway type. So we have motorways and the bigger rural roads in yellow, and the minor road network in black. And of course, we also have rail lines and public transport stops. The transport systems and modes available are conventional car, bus, train, and walk. We have 3 modes: car driver, car passenger, and public transport. and the same for the demand segments, but additionally we have one demand segment for the through traffic, which is also using the transport system conventional car. We will also have a look at the procedure sequence. So first, an assignment is initialized. We will also initialize all the demand matrices. Then we have some steps to calculate skims for private and public transport. Some of these matrices are then set as an impedance for modes. Then we will have the calculation of the travel demand. It's a tour-based model, VSEM. So we will have trip generation and combined trip distribution and mode choice. Then we will have the private transport assignment. Travel times are updated, and then we will step back and we'll feedback this into the travel demand calculation again. So we have some steps which will run in the loop for 3 times. Afterwards, the final skim matrix calculation and public transport assignment. So we will run this procedure, and as the model is rather small, this will only take a few seconds. And we will have a look at the network, and we can see that the network is loaded. So in dark green, we have the conventional cars, conventional car demand, which is calculated by the travel demand model. And the gray bars are the through traffic. So this over here is the static demand, which is not influenced by the travel demand model. So we already prepared the indicators for this, and we have prepared 3 indicators. So on the left, the trip-based modal split, in the middle, the total distance traveled, and on the right, the time spent in the network. And these consider only the calculated demand. The through traffic is not included. And we can see that all 3 indicators are dominated by the car modes with a similar distribution. So we have around 54 to 55% car driver. We have 18 to 19% for car passenger, and the rest for public transport. And these are our values for the baseline. So it will be interesting to see the results in comparison to the 2 other scenarios with AV. If we want to introduce highly automated vehicles, we have to make some changes to the model. So here's a general overview on what we are going to do and what we are going to see. So first, we need a new transport system with the name car AV. Then we will also have a new mode and new demand segment with the same name, but this we will only use for a specific skim calculation, and we will not use it for mode choice. So conventional vehicles and highly automated vehicles are both part of the mode car driver. The AV share in the network is set by the user. We will have no changes regarding car availability and trip generation. Traffic performance is assumed to be influenced by automated vehicles. The same goes for travel time perception, but this is only considered in scenario S2. And if traffic performance is influenced, travel times will change, and this leads to changes in destination and mode choice. And the first thing we are going to do in VSEM is to split the demand according to the AV share. So we will need 2 things for this: the AV share and the demand matrix for car driver. And what we are going to do is to multiply the respective share for the transport system with the total car driver demand. And this will give us a new demand matrix for conventional vehicles here, and the same with automated vehicles. So it's pretty straightforward, and the screenshot shows how this is implemented in VSEM. So we will have 2 new formula demand matrices. So now we are going to do exactly that in VSEM. So first we will run a script. The script adds a new transport system. So we now have automated car, and we also have a new mode and demand segment for car AV. And the other thing that the script did for us is to insert two new user-defined attributes. So one is on the level of matrices. This is just an identifier for if we add formula matrices later, these will use this attribute. And the other one is our AV share on a network level. Then we will run another script. This will create those two new matrices for us. So one for the conventional car demand and one for the automated vehicle demand. And now we also have to include AV in our private transport assignment. So we will go to the assignment procedure and include AV driver. So now how are we going to include AV regarding traffic performance? So our main assumption is that AV perform differently than CV, and to be able to account for that, we will use the passenger car unit concept. Passenger car units are a standardized unit for road capacity and traffic volumes. All vehicles need to be converted to passenger car units. So this is a common concept for macroscopic models. For example, one conventional passenger car corresponds naturally to one passenger car unit. A heavy-duty vehicle corresponds to two passenger car units. And if we look now at AV in red, they could correspond to something different than one, for example, 0.8 passenger car units. We can also extend this concept to have different PCU values for different roadway types, since we could assume that AV will perform differently on these different roadway types. For example, in CoEXist, we classified 3 roadway types: motorway, arterial, and urban street. But of course, this depends on the model and input data you use. In Visum, we need a new volume delay function, which takes AV with this approach into account. So we will switch back to Visum and run another script. The script adds 2 new attributes to the model. Both are on the level of links. The first one is AV ready. This attribute can be either 0 or 1. 0 means that a link is considered to be not AV ready. 1 means that the link is AV ready. And if a link is AV ready, an automated vehicle is able to operate in automated mode. If it's not AV ready, travelers have to drive manually in their AV. And the other attribute is our PCU factor for the transport system AV. So we also want to be able to modify these parameters in our procedure sequence. So we will add procedure parameters and read them additionally to our procedure sequence. So I added a group of 3 procedures. First one sets the AV share. So we assume, for example, 50%. This is just for demonstration purposes. Then our PCU factor for all links in this case, but you can also define conditions if you like. And third one, which link is assumed to be AV ready or not. Here we use if condition depending on the link type. And we can just execute this and have a look how we assumed this for this demonstration. So all links now with an additional green are assumed to be AV ready. These are the motorways and the bigger rural roads. All other roads are red, so travelers have to drive manually on these roads. And the rail is, of course, not considered at all for private transport. What we also need to do now is to add a new volume delay function. So we will go to General Procedure Settings, Private Transport Settings, and links volume delay functions. What we see now is we have a standard BPR function set here, and this is used for all link types. And what we want to do now is add a new one, which also takes AV into account. And we will choose a prepared user-defined volume delay function. This is working in the same way as a BPR function, with the difference that it is able to consider different PCU factors for AV. And if a link is AV ready, the value of our attribute is considered as this factor multiplied with the traffic volume. If a link is not AV ready, an AV will perform in the same way as a conventional vehicle and will have the passenger car unit of 1. We also want the volume delay function to behave in the same way as the original one, so we will adopt the parameters of the old one and we'll set this new function for all link types. Confirm this, and then we are good to go and run the simulation again. And now we can have a look at the network. So the network is loaded again. We see the conventional cars in the dark green. And now we also have automated vehicles in turquoise. And what's now important to notice is that although we set an AV share for 50%, this only counts for the calculated demand. So as we can see here, because of the through traffic, we will not have an AV share of 50% on all links. So we will look again at our indicators. So we have a tiny increase in the trip-based modal split towards the car modes. And for the distance traveled and time spent, we normalize the values to the base case to 100. So in the box above, we see the total changes. And the distance travel increases because on the one hand, we have a small modal shift towards the car modes. On the other hand, we will have changes in the destination choice. So we assumed AV to perform better than conventional vehicles. This means that travel times are decreasing, and then travelers are able to reach further destinations within a similar travel time. So our distance traveled will increase, and with the given assumptions, time spent decreases to a small extent, although we have a higher mileage of the car modes. But AV improve traffic flow and reduce the travel times. So this is decreasing. So now another topic that also needs to be addressed is the perception of travel time. If you are free to spend your time on other things than driving, for example, reading a book, watching a movie, writing messages, or something else, you will probably perceive the time in a different way. And this needs to be considered in travel demand modeling. So now it must be stressed that we are talking about highly automated vehicles. So they are still a transport system of the mode car driver, but they will influence the attractiveness of this mode. Our assumption for modeling is now that perceived travel time corresponds to the travel time in automated mode reduced by 30%. This is just an assumption from us, but it's inspired by values from literature and studies. So if you have a look, you will find stated preference or revealed choices surveys on that. So the question is now, how do we implement this in the model? I will explain the concept with this simple example. So we see one origin-destination pair, and we have one route connecting these zones. The roadway types are urban, the first and the last road stretch, and motorway in between. And the actual travel time is 5, 20, and 5 minutes, and it's perceived in the same way in a conventional vehicle. So our factor for perception in a CV is 1. If we now imagine a motorway to be AV ready, since it's a simpler road environment and easier to handle for a highly automated vehicle, now you are able to spend this time on non-driving tasks. So the 20 minutes will be perceived differently, and with our assumption that it is reduced by 30%, we will have a reduction in the perceived travel time. So we will have 24 minutes in comparison to 30 minutes for a conventional vehicle. And for the mode car driver, now we have to combine both according to the AV share, weighted with the AV share. So in the end, these 27 minutes are used as one part of the impedance for mode choice. So we will do this now in Visum. We will run another script. The script again creates user-defined attributes for us. One is the travel time, which is AV ready, so the automated travel time. This is a formula attribute. We will have a quick look at the formula. So basically, this attribute just adopts the current travel time for AV if the link is AV ready. And we will use this attribute later for a user-defined skim calculation. The other attribute we added is our factor for the perception in the in-vehicle time in automated vehicles. So now we will add additional procedures. So we want to be able to modify this factor in a comfortable way. So we will add a step here. So we can change this if we like to. I leave it at 0.7 as in the slide. And we will add another step for the user-defined skim calculation. We will also read this additionally. And so this step is just conducting a user-defined skim calculation for AV. And we will now have to define what this calculation really does for us. So we go to calculate general procedure settings again, to skims. Now we see in row 13, we have the user-defined skim. We can give it a name. And below here, we have to define the parameters for this skim. And we want to include on the link level the attribute we just saw, so our automated travel time is considered here. This attribute uses seconds as a unit, so we will divide it by 60 because we need to have the skim matrix in minutes, as you can see here. We confirm this, and if we now run this procedure and have a look at the skim matrices, we see that Visum created a new skim matrix for us with the name we gave it. And what's included here is the average automated travel time on origin-destination pair level. And now we we'll run one last script. The script creates 3 new formula matrices for us. I will not go into detail, but if you remember the simple example, these matrices just include parts of the total perceived travel time for both modes. So in the end, this is our final matrix for the perceived travel time for the mode car driver, combining the perceived travel times for conventional vehicles and automated vehicles. Now, the last thing we need to do is to set this as a new matrix for the impedance for the mode car driver. And now we will run the simulation again. We deserve a break, lean back, watch Visum do the work for us. Now, as we can see, the network is loaded again, so we have new assignment results ready. And we already prepared the indicators. So what we see now are similar trends as before regarding the share of car modes, but these are intensified by the assumptions on the perception of travel time we made. So the trip share increases, and yeah, the car modes seem to be more attractive now. This, on the one hand, leads to bigger shares of the car modes on the other 2 indicators. And on the other hand, the perceived time savings lead to a different destination and route choice. So this results in an increase in distance traveled. And also, do travelers spend now longer time in their cars? But people do not perceive this time as negatively as without AV, since they are able to spend some of the traveling time on other tasks than driving. To conclude now, on top, we have the technological development. So the automation level of vehicles will increase by time. This leads to cars that will become better and better and more attractive to us. The objective is that we want to understand the impacts on travel demand. So what is going to happen when highly automated vehicles are introduced? One solution is that we should extend existing travel demand models. So we need to supplement the models we already have and use today with the methods presented. So these methods enable models to show the impacts of automated vehicles on travel demand by permitting to analyze assumptions on traffic performance and travel time perception. And these methods only require rather small modifications of existing models. And with this, I would like to finish the demonstration and presentation. Thank you very much for your interest and your attention. And if we want to have a deeper look into the implementation, as a reminder, a download link covering all files used today will be distributed. And now we will have time for questions.
Exactly. Thank you very much, Jörg. This was a very complete and interesting presentation. As you just mentioned, we will send a link where you can download all these examples. This is going to arrive each participant tomorrow within the follow-up email. You will also receive a link when you can watch the video recorded and a short survey for your evaluation of the webinar, which we would very much appreciate if you can take a couple minutes to reply to. Okay, now we can take a couple questions. Let's see, here we have one question from Sakir Faramand. Is it possible to include spatial reference in this model for trip generation and attraction, such as a postal code?
I'm not sure if I really understand the question. But
Maybe
Yeah.
Would you like to clarify your question, Shakira? We can allow you to.
Maybe I can say something about trip generation.
Yeah.
So with the examples or the scenarios presented right now, we do not assume any changes in trip generation. So we don't assume that new trips will be generated because these AV are only considered to be highly automated vehicles. So at that point where you want to model fully automated vehicles, then this will change, because then people without driving license are able to also conduct trips with these vehicles. But for this example, we do not consider any changes in trip generation.
So the idea is that you plug in it to any existing travel demand model, and whether you code the postcode, this doesn't matter. If you do it in your normal travel demand model, you can keep it. So it's not about how to develop a travel demand model, it's about how to extend an existing travel demand model to include features of automated vehicles.
Perfect, thank you very much. And he would also like to know your opinion on including AV shared in the model, as he's currently doing some research on car sharing.
So the AV share, as presented, is a user input between 0 and 100%. So this just sets how you are going to split your original demand for car drivers. So your vehicle fleet will just be split, and it will be applied, this share will be applied on all origin-destination relations in the same way.
So you can experiment by varying it, and it's not about car sharing, it's about the share of cars which have this specific ability of private non-sharing cars which have AV capabilities. So they mean they use the capacity in a different way. And if you use it as a private driver, you have a different perception of travel time because you can do other things.
Great, thank you very much. We have one question for Peter now. Can the simulation be used for conventional vehicles? Here I want to understand that the person is referring to platooning. Of course, I mean, platooning by design is available only for automated vehicles.
Yes, that's right. But in Vism, you can have a mix of conventional vehicles and automated vehicles, and you can have different types of automated vehicles. So you can have a mix of, let's say, 60% of conventional vehicles and 20% of automated vehicles with cautious driving behavior, and 20% of vehicles with normal driving behavior, or any other mix of your choice. You just need to make sure that your conventional vehicles are in a vehicle class which is using the driving behavior for conventional vehicles. And the automated vehicles are using another driving behavior which is set for automated vehicles. And for example, they are also allowed to form platooning.
Perfect, great. Thanks for the clarification. See, we have a question from Eloisa Macero for Jörg. Is it possible to increase road capacity instead of changing the PCU for simulating CAVs?
Yes, this is also possible. It's then, yeah, a different approach, but I mean, if you know how many AVs you have and how their impact is, you can leave the PCUs as they are and change capacity. But the approach presented is quite flexible. So if you're not really sure how many AVs you are going to have on each link, it's easier just to say how one AV performs and how much capacity it claims or it needs. And if you have no AV at all, of course, nothing changes, even if you use the new volume delay function presented. But yeah, it's in general, it's also possible. It's an attribute. You can modify it as you like if you have good reason to do so.
Great, thank you. Okay, now before we take some more questions, let's just have one final poll. So, Serena, if we can launch the final question. Here we want to know your opinion on the impacts of automated mobility in the future. Do you think it's going to improve your city's mobility and it's going to support sustainability goals?
All right,
Okay.
votes are coming in slowly. I'll leave it open for just a couple more seconds. All right.
Great, thank you. So, as we can see, around half the people believe that it is in fact going to improve urban mobility. But of course, there's a lot of uncertainty about this topic. So about 30% can't really tell. And also this is why CoEXist is trying to fill in these gaps of methodologies and tools that might allow us to try to handle these uncertainties and get a better grasp on what might happen in the future and be able to address it on time. Thank you, Sidrina. Then let's see if we can take a couple of more questions before the webinar is done. So we have a question by Fotaini Orfanu. So are the deliverables referring to the microscopic and macroscopic models presented in the webinar public? And here we can say yes, we have various deliverables on not only how these tools can be used, so the user guides, but also the development process, how they were calibrated and validated and implemented within CoEXist. They can be found in CoEXist website under resources. And if you have any doubts about them, feel free to contact us through the contact option there.
I would like to add one information that there is a guide for AV modeling, and this one will be updated soon because platooning is not inside yet, but all the other features are.
Thank you. Yeah, this is very important to clarify. Through the project, there's been advancements in the tools. So by the end of the project in April 2020, we will have all final deliverables available in our website. Yeah, thank you. So do we have any more questions? Also remember that you can raise your hand and briefly pose a question. Okay, and as a follow-up question on the last one we just took, Sophia Sharon-Pidou is asking whether this guide is part of the deliverables of the project, the one you just mentioned, Peter?
Yes, it is.
Yes, it is. Yes, exactly. Okay. I think we just reached our 30 minutes. So as no other questions are coming in, I would like to thank you all for your attention. Thank you for the speakers for the great presentations. We're very happy that today we reached a very large audience. For a moment, we had over 90 attendees. It's great to see this amount of interest out there. Thank you for your attention, and I hope you follow up on CoEXist results and updates in our next event. Thank you very much and have a great day. Okay.